In this video, you're going to talk about application of exponential equations. In the previous examples, we saw how to solve exponential equations for the variable x, y, whatever the variable is, and now we are going to see what are applications of these exponential equations. First, we are going to define an exponential equation to be of the form y equal ab exponent x. In this case, when x is equal to 0, then you get y is equal to ab exponent 0. Remember that any number exponent 0 is 1, so you get a. A is the initial value, or as you recall, is the y-intercept. Now, the value for b, which is the base of the power or the exponential function, is the one which determines if you have a growing exponential function or a decaying one. If b is greater than 1, for instance, if y is equal to, let's say, 4 times, let's say, 3 exponent x, b here is greater than 1, then the function represents a growth exponential function, and when b is between 1 and 0, then it's going to show a decay exponential function. One example of b between 1 and 0 is y equal, let's say, 3 times 1 over 2 exponent x. Now, the real life applications involves in solving the exponential equation for variable x. Now, solving these exponential equations is not as simple as the previous lesson. Usually you use technology to find the value of x. And we are going to do a couple of examples and showing how the technology is going to be used to solve exponential functions or equations. In this example, we have the population of Ontario, which was 9.4 million in 1985. It is growing at the rate of 1.0125%. Now, this situation, we can model this using this exponential equation. Now, as you can see, when t is equal to 0, 1.0125 exponent 0 is 1. So the initial value is 9.4 million, which is exactly what the population is in 1985. And t represents the number of years past 1985. Now the question is, in which year the population first exceed 10 million? Again, this is the type of equation that we can't solve it algebraically, except if you know how to use the logarithmic functions on your calculator, which you don't. So what we are going to do, the first type, we are going to use divide and conquer. So I'm going to pick two extreme points, which one is less and the other one is greater than 10 million, which is going to result in greater than 10 million. If I pick t equal to 0, the population becomes 9.4. If I pick t equal to, let's say, 10 years, the population becomes 9.4 times 1.0125 exponent 10, which if you use your calculator it's going to be about 10.6. Now 10.6 is greater than 10 million that we want. So I'm going to pick a number now between 0 and 10, right in the middle. To find that middle number, I'm going to add 10 and 0, which is going to be 10, and then divided by 2. So it's going to be 5. So I'm going to start drawing my table as usual. So I'm going to make t equal to 5. If t is equal to 5, I'm going to get 9.4 times 1.0125 exponent 5, which is going to give me about 10, which we are lucky with one division we could find that value. So we can say that 5 years after 1985, meaning 1990, the population of Ontario exceeds 10 million people. In the next example, we have to redo the first example, which is about Ontario's population, but this time using a graph. As previous lesson, I'm going to use the site desmos.com. As you can see, I've already plotted one function, which is 9.4 times 1.0125 exponent x. And since we want to solve this one for x so that y is greater than 10, I'm going to plot the line y equal to 10. This is the graph of my exponential function. You can see that it's growing, and the growth, as you can see, because the base is 1.0125 and it's greater than 1, the exponential function is growing as it is apparent from the graph. The other function is y equal to 10, which is going to be this graph. Now, the point of intersection of these two graphs is the one that we are looking for, because after this point, going to the right, you can see that my population is growing exponentially. Now, what I want to know is what is the x-coordinate of this point, and the x-coordinate is equal to 5, which is exactly the same as what we got using divide and conquer method. In the last example, we have caffeine, which has a half-life of approximately 5 hours. What exactly is half-life is the amount of the time that the material loses half of its mass. For instance, in this case, caffeine is going to lose half of its mass in 5 hours. Suppose you drink a cup of coffee that contains 200 milligrams of caffeine. The question is that how long will it take in hours until there is less than 10 milligrams of caffeine left in your body? Now, to come up with the equation, there is no equation given here. We are going to draw a table of values which shows the time and the caffeine in your body. Let's say that time t0 initially. You can see initially there is 200 milligrams of caffeine. So 200. Then let's say after 5 hours. After 5 hours, we said that half-life is 5 hours. So this means the 200 becomes 100. Half of it is gone. Let's say after 10 hours. After 10 hours, 100 becomes 50. Now let's rewrite these in a different form. I can write 200 as 200 times 1 over 2 exponent 0. You will see why I'm writing it like this. In fact, usually when you are dealing with half-life, you always go by including half in your equation, 1 over 2. Let's write 100 in terms of exponents. I can write this guy as 200 times 1 over 2 exponent 1. 200 times 1 over 2 exponent 1 can also be written as 200 times 1 over 2 exponent 5 over 5, because 5 over 5 is 1. Also 0 is 200, 1 over 2, 0 over 5. 10 can be written as 200 times 1 over 2 exponent 2, because 1 over 2 exponent 2 is 1 over 2 times 1 over 2, which is 1 over 4, and 200 divided by 4 is 50. I can also write this one as 200, 1 over 2, 10 over 5. If you look at the time and the exponent here, you can see the reason that we are writing it like the one that we have written so far. So after t, let's say t hours, the amount of caffeine is 200 times 1 over 2. You can see that the exponent here goes with the time divided by 5. So I can write t over 5. For any value of t, the amount of caffeine in your body is 200 times 1 over 2 t divided by 5. Now we have to solve this equation for values of t when the caffeine is less than 10 milligrams. Now we are going to use the equation that we derived previously, c equal to 200 times 1 over 2 exponent t over 5, to find the value of t which makes c as close as possible to 10 but less than 10. So again, as usual, I use the divide and conquer, because using graphing or technology is good, but if you don't have access to the technology like your unit tests, it's better to get used to a method like divide and conquer. So I'm going to start this time by drawing a timeline and pick two values. I pick 0, t equal to 0, and let's say I pick 50 for t. Now, when t is equal to 0, it's going to give me the initial value, which is 200. When t is equal to 50, I'm just going to put in this equation t equal to 50 and then simplify using the calculator. If you do this one, then what you're going to get for c is 0.2. Now, as you can see, 200 is much greater than 10 and 0.2 is much less than 10. But we need some value for t that makes c very close to 10 but less than 10. So what I'm going to do, I'm going to pick a midpoint here. And the midpoint is going to be 0 plus 50 divided by 2, which is 25. Now I'm going to evaluate this equation again. For t equal to 25, if you use your calculator, you will find this value is 6.25. Now, just looking at this timeline, you can see when you go to the right, closer to 50, it gets smaller. The value of c gets lower and lower, but when you go to the left of 25, close to 0, the value gets bigger and bigger. Now we have 6.25, which is less than 10, but we want to be as close as possible to 10. So I'm going to pick a value between 25 and 0 because I want to make it bigger than 6.25. So 25 plus 0 divided by 2 is 12.5. If you evaluate the function c for t equal to 12.5, you get the value is, for c is 35, 9.4, which is this time, which is greater than 10. So I have to make it smaller. So what I have to do is to find the midpoint between 25 and 12.5. Again, add 25 and 12.5, then divide by 2, you get 18.75. Now, 18.75, if you evaluate the caffeine in your body, is going to give you 14.9. Now 14.9 is greater than 10, so we have to make the value a little bit smaller. So I'm going to pick a number for t between 18.75 and 25. So add these two divided by 2 and you're gonna get 21.9. Now if you find the value of C becomes 9.6 now, which is getting close to 10. Now we can even stop, either stop here or just continue. I'm not going to continue anymore. 9.6 is close enough to 10. So we are going to say that after about 21.9 hours, you will have less than 10 milligram in your body.